Okay, everybody, we are at the last lesson of the year. So you should have your packet for the second part of the organic unit. And we are looking at the very last lesson, which is what are different types of organic reactions. So now we're going to put together the different types of organic compounds that you've been looking at on reference tables Q and R and put these into the context of chemical reactions. So these do now questions. You should have reference table R and your outline handy to get these done. So for the first one, draw 3-pentanol. The first thing you need to look at here is the word, okay? The ending of the word ends in OL. So you need to go to reference table R and you need to figure out, using table R and the examples they give you, what kind of compounds end with the two letters OL, all. So what you should see there is that this represents the ending for an alcohol. So then you look on table R and you see that an alcohol has the functional group of an OH attached to a carbon. Now we need to use reference table P to figure out how big this molecule is. So we go to reference table P and we look up the prefix pent. The prefix pent represents the number 5. So I'm going to put 5 carbons in a row, connecting them with single bonds because this is a pentane-based molecule. And then I need to attach this OH group. Well, where do I attach the OH group? That is also given to us in the name. I will attach the OH group to the third carbon. It doesn't matter if you attach it on the top or the bottom. And then every carbon has to count to 4. So I have to fill in hydrogens in all of the missing spots. Excuse me. So that is a 3-pentanol molecule. Now the second one, name this compound. So to name the compound, you need to do a couple of different things. You need to figure out the length of the carbon chain. Then you need to identify what makes this not a hydrocarbon, which is going to be that double bonded oxygen. And use reference table R to name it. So what I know with 3 carbons is that, and they're single bonded, that this molecule is based off of propane, okay? Now, though, this has a double bonded oxygen, and the double bonded oxygen is not on the end. So I have 2 options. When I have a double bonded oxygen, it can be an aldehyde, this is using table R, or it could be a ketone. The placement of that double bonded oxygen will tell us which category that falls into. So when we have a double bonded oxygen that's not on the end of a carbon chain, that will be classified as a ketone. So to name a ketone, I look at the example they give me on the reference table. That shows me how to put the name together. The ending of a ketone has to be -one. Okay, so that's propanone. Now the last one here, draw propanal, I have to use the words to help me. So I know based on the first part of this word that it's going to have 3 carbons with single bonds. And I know that based on the last part of the word, Al, that's going to make it an aldehyde. Three carbons single bonded. Aldehyde has to go on the end. It doesn't matter which end. This is annoying. I'm sorry about the coughs. Then I need to complete each carbon so it has 4 bonds. Now be careful because this last carbon already has 3. It's only going to get 1 more hydrogen attached. Now we can jump into the organic reactions. The first type of organic reaction that we're going to look at is called fermentation. Fermentation is something that you were taught in living environment. Fermentation is when you take a glucose molecule and it breaks down into ethanol, and I know this is ethanol because it has 2 carbons and it has an OH group at the end, and carbon dioxide. This is always going to be the equation for fermentation. You would not have to write this equation out from scratch. You might be asked to balance it. You might be asked to classify it. You will always have glucose. You will, on the reactant side, you will always have ethanol and carbon dioxide on the product side. This happens with yeast. Alcoholic fermentation is what yeast will do when it breaks down glucose anaerobically. This is used in baking to make bread rise. It's also used to produce alcohol. The next type of organic reaction is combustion. Combustion reactions are when you have a hydrocarbon. Remember, hydrocarbons only contain hydrogen and carbon. It will react with oxygen. It will always form carbon dioxide and water vapor. Those are going to be the products of your combustion reaction. This is a Miss Winter joke. Crying and breathing a lot when you're combusting and you're nervous, okay? Those are always going to be the products. There's two different types of combustion. There's complete combustion and there's incomplete combustion. Complete combustion will happen if you're in an open system and there's enough oxygen around to get that hydrocarbon to fully break down, so you get carbon dioxide. If you're in a closed system that has a limited amount of oxygen present, instead you're going to get carbon monoxide. That's what happens in a car engine. So that's why car exhaust, or even like your furnace, that's why they produce carbon monoxide, is because it's in a closed system and there's not enough oxygen present to fully break it down. That's why it's important to have carbon monoxide detectors in your home, because if that carbon monoxide escapes your furnace and gets into your home, it can be lethal. The next type of organic reaction is called saponification. Now, saponification is a wild-looking reaction, but what you need to look at are the first four letters here. If I rearrange the first four letters in saponification, I get the word soap. Saponification is the process by which a very large molecule, this is going to be a fat or a lipid molecule, reacts in the presence of a base, and it produces, this is known as a soap, and then a glycerol molecule. All you would never, ever, ever have to balance one of these equations or even recognize them. You would see this as a multiple choice question. It would say, which of the following reactions produces soap? Saponification. Okay? So don't worry about, knowing what these formulas are or anything. Just know that saponification is the process that makes soap. All right, these next two reactions, substitution and addition, are a little more detailed, but they're actually very easy to look at here. Okay, so if there's a substitute, that means that something has come in to replace something else. So what happens here with a substitution reaction in this example here, what you have is one of your reactants is going to be a hydrocarbon. Specifically, it's going to be an alkane. Now, what do I know about alkanes based on my reference tables and the kind of bonding that they have? An alkane is going to have single bondings between the carbon atoms. So what we have here is an alkane. In this case, this is ethane. I know that because there's two carbons. And it's reacting with a fluorine molecule. So here's a fluorine molecule. So what happens if you look at the products is that we're doing a swap. One of the fluorines, the fluorine molecule is going to break apart, okay? And one of the fluorines is going to latch on to where a hydrogen was. And the hydrogen that was there is going to get kicked out and bond with the remaining fluorine. The key with substitution reactions is you're always going to have two reactants and you're always going to have two products. This is called a substituted hydrocarbon. Like, I'm just putting one fluorine in its place. There is the really important thing to notice here, and I think this is on the next slide, there is no change in the carbon-to-carbon bonds. The carbon bonds are single, they stay single. So what you need to remember about bonding here is that saturated hydrocarbons have single bonds between them, and they undergo substitution reaction. Okay? Saturated hydrocarbons have single bonds between the carbons, and they undergo substitution reaction. So I'm not changing the bonds between the carbon. They are single, and they stay single the whole way through. I'm just popping off a hydrogen and plopping in this case, a fluorine. That's what it's showing here. Replacing a hydrogen from an alkane with another atom, it's usually a halogen. So there's no change in the carbon-to-carbon bonding. This is just a video that shows it breaking off and coming back together. I don't even know if that would work. Okay, now this type of reaction called addition, look at what we're doing here. Think of that arrow as your equal sign. I am taking In this case, I'm taking a molecule, a hydrocarbon that has a double bond between it. So using your reference table, table P and table Q, what is the name of this hydrocarbon? It would be ethene, because there's two carbons and there's a double bond between those carbons, making it an alkene. So what we're doing here is we're taking this alkene, which is unsaturated. Unsaturated hydrocarbons don't have just single bonds. They'll have double bonds in them or triple bonds in them. And I have this fluorine molecule again. But instead of ripping off a hydrogen and plopping in a fluorine, look what we're doing here. We're changing the bonding structure between the carbon atoms, and we're taking what was a double bond and turning it into a single bond. And by doing that, we're freeing up spaces where the electrons are present in order for those fluorines to jump in. So I'm just going to redraw this using dots to represent the bonds. Okay, I'm going to leave the hydrogens alone because they're not involved in this at all. They're just hanging out. Okay, so here is one of the bonds and here is the other bond. And I want this fluorine molecule to become incorporated, this whole molecule to become incorporated into this. There's no room. Okay, carbon counts to 4 and it's done. There are no more spaces, there's no more electrons available to form bonds with these fluorines. So what has to happen here is that in order to free up these electrons, this bond has to break. When that bond breaks, now I have an electron here and I have an electron here. What then happens is these fluorine atoms, that molecule breaks apart, okay? This molecule is going to break apart. So now I have a fluorine, and there's actually 7 valence electrons, but we're simplifying this. Now I have each of these fluorines with an available spot for bonding, and I have each of these carbons with an available spot for bonding. So what I end up having on the product side, all of my original stuff is going to be in red. Okay, so here's my carbons. Now they only have a single bond. There's my hydrogens that were originally present in the molecule. That's not changing. Then I have those extra electrons that formed that were kind of like made available when that second bond broke. And I have now places for those fluorine atoms to come in and bond with those carbons. So I end up with what's on this picture down below here. I have carbons that are now single bonded together. I have the 4 hydrogens that were present originally, and I have these new fluorines that now had space available to jump in and join this party. So what an addition reaction does, I'm adding my 2 reactants together to make one product. And I can only do that by changing the bonding structure. If I had a saturated hydrocarbon, it was already had single bonds, there would be no places to free up space for things to jump in. That's why they can only do substitution. But with addition reactions, you can take a double bond, turn it into a single bond, and free up places for something new to come in. You could take a triple bond and change it into a double bond and free up spaces for stuff to come in. So when you're dealing with addition reactions, you have to start with something that is either an alkene or an alkyne. You need to break one of those multiple bonds, change the bonding structure in order to join that other molecule in to make only one product. Okay? So again, with substitution, we don't need to change the bonding structure between the carbons. We're just plopping one thing in and taking something out. With addition, we have to change the bonding structure in order to get that other molecule to get added in. So that's the difference between them. The next type of process is called esterification, and I mentioned this to you when we talked about esters. With esterification, you're going to always have this category of compound. Now, this category of compound, look at reference table R. We have a C with a double bonded oxygen and then an OH group. What kind of compound is this on table R? This is an organic acid. Okay? That's an acid. This one, the picture got messed up here. The bonds are all shifted around. This is a typo. We're going to pretend these things are, well, that one was okay. Shoot. This got shifted over. This should be here. And this should be here. These hydrogens that I'm writing in, these blue ones, should be attached to the carbons. This is just a formatting issue. Okay. So anyways, this other reactant has an OH group. So based on table R, what are we dealing with here if we have an OH group? This is an alcohol. Now, when the alcohol and the acid come together, we can't just link them together. We have to do what's called dehydration. Dehydration, remove water. And then as a result, we can join those two molecules together. When we join those two molecules together, we have this new functional group, which on table R, that would show you that it is an ester. So esterification is taking an acid and an alcohol. You have to take out an H2O. Here's my H2O to link these things together. When I do that, I form an ester, and esters give us things like fruity flavorings and scents. And that just shows you the same thing here. Okay, this last type, oh my gosh, it's the last type. Yes, it is. The last type of reaction here is the process of taking small molecules and making large molecules. So when you see the prefix mono, you should think one. When you see the prefix poly, you should mean many, right, or multiples. So this is very important in biology and biochemistry. Again, you learn some of this in living environment. That the key organic nutrients are carbohydrates, nucleic acids, proteins, and lipids. Those are very, very big molecules, but they're made up of very, very small subunits. The monomer of a carbohydrate is a monosaccharide. For a nucleic acid, it's a nucleotide. For a protein, it's an amino acid. Talked about those. Amine acid. And then for lipids, they're fatty acids and glycerol molecules. And then they can get put together to make what are called polymers. So the process where you take small molecules and make polymers is very creatively called polymerization. So polymer, just think huge molecules. So you should know that amino acids come together to make proteins, and glucose molecules make carbohydrates like starches. And if I have many esters, what's the prefix for many? Poly. So what do I make if I have many esters? Polyester. You know what polyester is? It's a fabric. A lot of your clothes are made out of polyester, sports uniforms and things like that. Okay? So that's where it comes from. It's a polymerization reaction. There's two different types of polymerization. You really don't have to know much about them. One of them is called condensation polymerization. Anytime you see condensation, you think, okay, there's water dripping out of it. So when condensation polymerization occurs, you can link the monomers together by removing water that frees up spaces for them to bond together. The other type of polymerization is called addition polymerization. We just talked about addition reactions. In addition reactions, you got to change the bonding structure to get stuff to link together. This picture came right off of a Regents exam. It was like, oh, what kind of reaction is this where you take, or N is equal to a very large number. When you see very large number and you're just repeating this thing over and over again, you're making a polymer. It's a big molecule. Things like plastic, nylon, Kevlar, those are all made, Teflon, those are all made through polymerization reactions. I will actually go over these couple of questions with you in class. All right, so thanks for listening. Hopefully you took some notes on this. Have a great day.